Thank you both so much for this invitation to speak. I hope you really enjoyed Alvaro's talk. That's a really hard act to follow. This is not going to be quite as flashy because I don't know how to use those fancy slide making techniques. It's going to be a bit more standard, but the math is really beautiful. I think it's a real privilege to study number theory. It's one of the oldest branches of mathematics, and it only keeps getting more exciting day by day. So I'm going to advance the slide, and that's totally going to work. Press this button. Kind of skip them. So I should use the. Yes, it's all right. So here are some phenomena to kind of lure you into the subject I'm going to talk about, which is called complex multiplication. And this is one of my favorite examples. So I've got a polynomial for you. Here it's x squared plus x plus 41. What we're going to do with this polynomial is just plug in the first few values, which are integers starting from 0. So let's do this in a run starting from x equals 0. And the pattern goes like this. We started 41, and then you add 2, and then you add 4, and then you add 6, and then you add 8, and so on, going all the way up. The last one in the run is 1601. What do these numbers have in common? They're all prime. And you maybe have a sense that primes are common, but they're like not that common. And it's kind of hard to find formulas that just spit out primes. But here's an instance where a polynomial that's very simple just spits out a whole run of 40 of them. Does the pattern go on forever? No, because if you plug in 40 and you do the math, you get a 41 squared. That's not a prime number. But I think this is a phenomenon that demands explanation. There's lots of different ways of displaying this behavior. If you write the integers around and around in a spiral and highlight all the primes, you'll see this one appearing as a diagonal. That's called an Ulam spiral, and you can look it up. There's a few videos about it. So I wanted to explain this phenomenon today. So this is not an isolated example. I give you a couple of others. There's x squared plus x plus 17 and x squared plus x plus 11. They act similarly, although since those numbers are smaller, the runs are going to be shorter. So they're not quite as impressive as this last one. And so, the question I want to pose is like, is this a coincidence? Spoiler alert, no, it's not a coincidence. It's an explanation. Okay, and then in this next slide, here's a kind of random constant. It's the square root of 163, and then I multiply it by pi, and then I raise e to this power. And it's kind of as random a number as it gets, kind of throwing together a bunch of numbers that I know to be irrational. This number is known to be transcendental. It's not the root of any polynomial with integer coefficients. Nonetheless, this number, if you plug it into a sufficiently good calculator, here's what you're going to find. There's going to be an integer part to it. And the integer part, you could factor away a large number that happens to be a cube. But forget about that. The rest of it is 743.99999999999. That is 12 nines. And then some not nines. So this number, e to the pi 163, it's very, very, very close to an integer in a way that really kind of leaps off the page and demands an explanation. So what is going on here? And once again, this is not an isolated phenomenon. So the constants with 67 and 43, that's going in the place of the 163, also work this way. But you'll find if you plug them into a calculator, there's not going to be as many nines. So it's a less strong example of the phenomenon, but it really is the same pattern. So the coincidence. And how do we relate this to what happened before? So the big surprise of this talk, which I'd like to explain, is that these two phenomena are actually related to each other. And one superficial way I can get across this relationship is that the numbers that appear here, 163 on this page and 41 on the last page, are related. Here's how. The polynomial x squared plus x plus 41 from the first slide, when you try to find the roots of that polynomial, you use the quadratic formula, you get this. And so there's that 163 up here. And the other two polynomials work the same way. those polynomials had the 17 and 11, and those spit out a 67 and a 43. So just in a straightforward way, using the quadratic formula, you could get these numbers like square root of 163 to be related to these polynomials that seem to be prime generating. Okay. All right, so what's going on? So I wanted to start with the first phenomenon about the prime generating polynomials, because that's a little easier to explain. And the theme of that phenomenon has to do with the concept of unique factorization, like unique factorization of integers into primes. That very well-known phenomenon, especially its extensions into number systems beyond the integers, right? So let's rewind. Let's take this topic all the way back to 1640. Breaking news. Fermat proved something that many centuries ago. So this is Fermat's famous two squares theorem, and it says that a prime is the sum of two squares under exactly two conditions. Like it could either be 2, which is 1 squared plus 1 squared, or if it's odd, it has to be 1 more than a multiple of 4. And it's an if and only if. So the primes which are 1 more than a multiple of 4 are the sum of two squares. And Fermat went further than this and figured out which just numbers are just sums of two squares. But the hard part of that reasoning is figuring it out for primes. Now, one direction of this implication is easy. The remaining primes are of the form 4n plus 3. And if such a number is a sum of two squares, you could do a little arithmetic mod 4 and get a contradiction. So one of the directions of this implication is easy. The hard part is showing that an odd prime of this form is always a sum of two squares. After all, where are the squares going to come from? So Fermat proved his theorem with this technique he called the method of infinite descent. And then Gauss came along and invented whole branches of number theory. But in doing so, gave us a framework for understanding Fermat's theorem in terms of unique factorization in extensions of the ring of integers. So the extension that is relevant to this theorem is the ring of Gaussian integers. We saw it appear in Elber's talk, but here we go. So the Gaussian integers, they're a set of complex numbers. They're the set of all numbers of the form a plus bi. The a and the b are integers. So if you were to just write them out or graph them, you would see a lattice, a square lattice inside of the integers, where the dots are kind of evenly spaced. These form a ring. You can add 2 of these and multiply 2 of these and get another one out. So a few quick definitions about working with Gaussian arithmetic. So ordinary primes, I mean like primes that are like integers, sometimes they factor when you move them into Zi. And a good example of this is 5. 5 is prime, of course, but in Zi it's sort of no longer prime. In fact, it falls apart into the product of 2 other numbers, 1 plus 2i times 1 minus 2i. So you can no longer call 5 prime in Zi, in fact. And so the right term that we use, maybe instead of prime, is irreducible. So here comes some more technical definitions. First of all, you have units. The numbers in Zi which are units are 1, -1i, and -i. And these just mean that you're allowed to divide by them. Like if I were to divide 1 by I would get -i, which is still a Gaussian integer. And you can only do that with these 4 numbers. All right, so here's a new notion. It's irreducible in Zi. It's sort of like prime. It means it doesn't factor. And the way that it doesn't factor is that you can't factor into 2 other Gaussian integers, neither of which is a unit. Of course, you can always factor out I. You can always factor out any of the units, but that's not the kind of factorization we're talking about. So as an example, 5 is not irreducible, but 1 plus 2i is irreducible. You can't take 1 plus 2i and factor it any further. Are there any questions on these notions so far? So sometimes numbers are prime. You can move them into Zi and they also continue to be prime, but you can factor them into irreducibles, it turns out. So the theorem that Gauss knew was that, so I'm calling this the theorem of unique factorization, although it's sort of a shorthand for what you might think of as that property. It goes like this. If you have an irreducible pi, and it divides a product alpha times beta, then it has to divide alpha or beta. And if you really think about it, this is the key factor using when you show that factorization into irreducibles is unique. You know, maybe I hope it's believable if I take any Gaussian integer. Either it's irreducible or it's not. If it's not irreducible, factor it. If those factors are not irreducible, factor them. Keep on going. At some point, it has to bottom out, it has to stop, and you express the thing as a product of irreducibles. Was that expression unique? Well, if a product of irreducibles is another product of irreducibles, then you do a process where you pick one of the irreducibles on this side, it divides a product on the other, and then you apply this theorem. It would have to divide one of the factors, and you continue canceling out irreducible by irreducible until you see that the two factorizations were actually the same. So that's why I'm calling this, for the purposes of this talk, unique factorization. So ultimately, this theorem powers the unique factorization of Gaussian integers into irreducibles. How do you prove this kind of fact? Well, the proof mirrors, it parallels the same proof for ordinary integers. There's a standard proof you might learn about in an undergraduate class in number theory that uses Euclidean algorithm. And the Euclidean algorithm is still valid in the Gaussian integers, it turns out, and you can make a step-by-step proof of unique factorization this way. So as an example of unique factorization, the number 5 divides the number 65. And 65 factors this way. 1 plus 8i times 1 minus 8. And 5 doesn't divide 1 plus 8i or 1 minus 8i. And it's actually pretty easy to see, because if it did, it would have to divide both 1 and 8. But it divides neither of those numbers, okay? So by unique factorization, what could you conclude? Well, 5 couldn't be irreducible. And indeed, it's not. We already saw that it factors into irreducibles like this. So this is going to kind of keep this logic in mind. It's going to power our proof of Fermat's theorem. And here's a note. The theorem of unique factorization is not at all universal. You can't take it for granted. So in a related ring where I is replaced by the square root of -5 instead of the square root of -1, 2 divides the number 6. And 6 factors this way. It's 1 plus root -5 times 1 minus root. But 2 divides neither of these factors, it turns out. And yet 2 is irreducible. You can't factor 2 any further in the ring c squared of -5. I mean, that statement requires proof, but the proof is not very hard. There's just no such factorization. So some rings have the property of unique factorization, and others don't. All right, back to this theorem. So the proof of the interesting direction, where you start with the prime of the form 4n plus 1, and you try to get it to be a sum of two squares, well, an efficient proof is going to borrow some techniques from abstract algebra. So let's consider, okay, we got z mod pz, that's a ring. The star means that that's the units in that ring, and that's a standard fact in number theory is that this is a cyclic group. The order of that group is p minus 1, and that's divisible by 4. So we have a cyclic group of order 4, and there's always an element of order exactly 4. You could take a generator and raise it to the nth power. And then that element, you know, when you, okay, I maybe skipped a step here, but the element, when you raise it to the second power, gives you an element of order 2. And there's only one element of order 2, it's -1. There can't be any others in a cyclic group. So x squared has to be -1 in that group. So x squared is congruent to -1 mod p. Thus p divides x squared plus 1. And that's the kind of key. I would call this the reciprocity step of the proof. We kind of just proved a case of quadratic reciprocity, showing when -1 is a square. So now here comes the step that's like, Fermat would have called this the descent step. P divides the number x squared plus 1, but it factors as x plus I times x minus I in the Gaussian integers. But P doesn't divide either of the two factors. It doesn't divide I. I mean, it doesn't divide x plus I, because if it did, it would have to divide the 1 coefficient, which is x. Okay, fine. But it would also have to divide the I coefficient, which is 1. But that's absurd. So it divides a product, but neither of the factors. So that means it can't be irreducible. That's what unique factorization says. So it has to factor. P is alpha times beta. So we factor. Those elements are non-units. Okay, so here's what we do next. We want to kind of bring everything into the realm of integers. So here's a definition. The norm of a Gaussian integer is defined this way. You know, it's a complex number, so you can take its absolute value and then you could square it. It's like the length squared of a vector. And that's a squared plus b squared. And a and b are the real and imaginary parts. So the norm is multiplicative. It's not so hard to see. You just have to believe that absolute value is multiplicative. It's also integer valued. So if I took the norm of both sides of this equation, I would get p squared is equal to the norm of alpha times the norm of beta. Alpha and beta are non-units. That means their norms are bigger than 1. So p squared is the product of two integers, and each integer is at least 1. There's only one possibility. All the integers are p. So p is equal to the norm of alpha, and that's a squared plus b squared. Boom, done. And it's a very interesting proof because it's not an algorithm for finding what the factorization is, what the a and the b are. It just kind of works, just powered by unique factorization, but it's sort of not algorithmic. All right, other questions on this chain of reasoning that we just proved? Pretty standard stuff, I guess, branch number theory. So now I can start to give an explanation for this prime generating polynomial. So this is x plus 41. So what's special about this polynomial? So let's first extract the root of it. And I'm going to call that root eta. So here's one of the roots. It's called eta. And I'm going to make a notation. I'm going to say z eta, or z adjoin eta. It's a subset of the complex numbers, a plus b eta, all of the ones of that form, where a and the b are integers. And you know, it's easy to see you could take two such complex numbers, add them together, get a new number of that form. But it's also closed under multiplication. If you multiply two such numbers, and you multiply everything out, you're going to eventually get, when you FOIL this out, an eta squared term, but eta squared is this. So after doing all the math, you get this. So that kind of demonstrates that the ring Z eta really is a ring. It's closed under addition and multiplication. So we consider arithmetic in this ring. There's also a norm. The norm of an element is still defined this way. It's the square of the absolute value. And just if you write out alpha this way, the norm ends up being this. And this is a quadratic form in two variables, a and b. So one thing I want to point out is that this norm is actually pretty big. If the number b is not 0, in other words, if alpha is not a real number, then the norm, here I completed the square, and if you just forget about this thing, the b is at least 1, and so b squared is at least 1, and then so the norm is at least 163 divided by 4. Okay, whatever, that's at least 40. It's bigger than 40, in fact. So the norms of non-real elements of this ring are all bigger than 40. Okay, fine. The real power behind this property of this polynomial is that this z eta also has the property of unique factorization. Now, I'm not going to be able to prove that in these slides. It's not as easy as saying that there's a Euclidean algorithm, because I don't think there is for this ring. But there are techniques by which you can check that such a ring has this property. Actually, I really thought about this while I was at the Ross program with Keith, and I actually really thought about this a lot. And I was like, you know what? I'm going to turn this around and go the other way. I want to show that if you can just check that this number is prime for the first few values, then the logic goes the other way. And you can show that this has got to be a unique factorization. But anyway, that's tangential. So here's the thing. Suppose x is an integer in the range 0 to 39. Then plug it into the polynomial, and the number is between 0 and 41 squared. And if that number is prime, okay, well, then it's prime. But if it's not, then it's composite. It's the product of two numbers, p and q. And then, you know, the product of those two numbers is less than 41 squared. So they can't both be bigger than 41. At least one of them has to be less than or equal to 40. And then this number p, it divides this number. But then this number, it turns out, factors. It's x minus eta times x minus eta bar. And then the same kind of logic is going to apply. If p divides neither factor, then p must divide. Then I guess it has to factor itself. Like it can't be irreducible. So it has to factor. P is alpha times beta. Take the norm of both sides, and you're going to quickly see that p squared is the product of two numbers. Neither of them is 1. So p has to be the norm of both of them. But the norm is bigger than 40, but it's also less than or equal to 40, and so we got to cut. So that proof shows that x squared plus x plus 41 is a prime, and we didn't have to do any checking of that. So it's true. It all just flows out of the fact that this z eta is a unique factorization domain, unique factorization. We good? Okay, elliptic curves. Good thing we already saw a bit about elliptic curves before, because I want to give some explanation for this other fact about e to the pi squared root of 163. You might say that's maybe the more shocking of the two strange facts. And here's how I'm going to motivate elliptic curves themselves. Let's start with calculus. So let's suppose you have a kind of calculus problem. It's determine the length of an arc. And you could do the complete unit circle, and that would be 2 pi. That would be the whole circumference. But suppose you just want to go t of the way. And by that, I mean, let's connect 0, 0, and let's go counterclockwise to a point like this, where the y-coordinate is t, and the x-coordinate has to be that. And if you set up the arc length problem, you find that it works out to be like this. And that's no big deal. You have to do a trig substitution, and you find that it's arc sine of t, and that makes sense because that's kind of what sine is trying to do. It's like when you take sine of an angle measured in radius, that's supposed to be giving you like the x-coordinate, or sorry, the y-coordinate, and this t was the y-coordinate up there.
Shouldn't that be dx?
Oh my God, it should be dx. I sent everything through Keith. I didn't sound like I asked him. Asked me to find all the typos, but I sent you the slides. Okay.
Find as many as I found yesterday.
You found many, many typos. Thank you for that. So the complete integral is what you would get when you kind of take t all the way around the semicircle, and that would be pi over 2, the arc length of it. Oh, sorry, the quarter circle. That would be equal to. Oh, this should actually be 1. That's like another sine inverse of 1. Or you could say let t is equal to 1. Okay. So here's an amazing fact, although if you think about it long enough, it's like not that amazing. But the thing with sine, so if I just kind of naively define sine, it's like, oh, here's this integral. It's just, I mean, this is kind of a way to invent the sine function. It's like, here's this integral, and then integral is some function. And then take the inverse of that function. That's what sine is. I mean, that's how one-way calculus could invent the sine function for you. And then if you plug in a rational multiple of this pi over 2, so I could phrase that as sine of q pi, where q is a rational number. Then an algebraic number has to come out. Like the root of some polynomial with rational coefficients has to be come out. And as an example, sine of pi over 2 is this one. It's like every student of trigonometry knows this. But this one's not as well known. Like the sine of 2 pi divided by 5, so that's 1/5 the way around the unit circle. So that's 72 degrees. Sine of 72 degrees is that number. And that's an algebraic number of degree 4. And it's a really good question. Like, wait a minute, what's going on here? Why are they all really like this? Will sine of 2 pi over 7 be like that? The answer is yes. But I just want to give you an interpretation here. The point on x squared plus y squared plus 1, that curve, which is like q of the way around, that has algebraic coordinates whenever q is irrational. So it has algebraic coordinates whenever you go a ratio around the unit circle. Now, okay, the fact is not that surprising, actually. I mean, you could prove it like this. So there's a relationship between the sine function and this exponential function e to the ix. Okay, here it is. And then if I just plug in the number pi times q into this, I get e to the pi q. And then that q has a denominator. And if I take this number to the power of that denominator, I'm going to get e to the I pi times the integer. That's plus or minus. So already you can see that this number is algebraic. It's the root of some polynomial like x to the n equals to 1. So then you just have to know that the sum of two algebraic numbers is also algebraic. So that's true. But I mean, this fact is not so surprising with a little bit of abstract algebra. For abstract algebra, this number generates an abelian extension of Q. So if you would join this number to Q, you get a finite extension of the rational numbers. That extension is Galois. That Galois group is abelian. It's commutative. And there's some cool thing called the Kronecker-Weber theorem that says that every abelian extension can be achieved. It's found inside of an extension obtained this way. So there's a really satisfying theory of extensions of the rational numbers, which are abelian. It's completely known what they all are. So it's funny that Hilbert's problems came up because here's another one. So we already learned about Hilbert's 10th. Here's Hilbert's 12th. So motivated by this, can we generalize e to the 2 pi I x to other functions, other transcendental functions? So that specializing x in some way generates extensions of number fields, especially the abelian ones. So Hilbert was drawing on the fact that class field theory was kind of recently established, and that's like an abstract classification of all of the abelian extensions of the number field, but it doesn't really give you what those abelian extensions are. Like maybe you want formulas for them. You know, this Hilbert asked, well, why can't we do this for number fields other than Q? So Kronecker's Jugendtraum, or like dream of youth, was to find a solution to this problem, at least when the base field, the number field on the bottom of this, is an imaginary quadrant. So, okay, here comes hard stuff. So it's like, I wanted to set up an analogy between the circle, which just invented the sine function, and an elliptic curve, which invents another function, an elliptic function. So I write down this integral. So you could just take it for granted that this integral is interesting. But I'm going to submit to you that if you try to figure out the arc length of a certain ellipse, I'm not going to tell you which ellipse, but if you try to find the arc length along it to some degree, this kind of integral could come out. And if you try, there's no method of trig substitution which solves this integral. It's just its own thing. So a lot of 19th century mathematics like approaches problems like, what is this integral? How do you integrate a general algebraic function? And even though it can't evaluate it in terms of elementary functions, it still wants to deal with those functions. So let's formally do what we did to invent the sine function. We say that this function of t, let's write it as the inverse s function, just like the function before was the inverse sine function. And let's also define a certain constant. Let's call it var pi, because that's what that symbol is. It's like a variation on pi. Var pi over 2 is this thing, just when you have it into complete integer. And that's relevant to the complete arc length of the ellipse. And okay, so it happens to have some evaluation in terms of like a gamma function or whatever, but we don't need it. So s of pi over 2 is 1 in the same way that sine of pi over 2 is 1. All right, here are the amazing facts. Here's it. So if I plug in pi over 3, the s function gives you this number. If I plug in pi over 4, the s function gives you this number. They all seem to be algebraic. Furthermore, it's not necessarily true when I adjoin these numbers to Q, I get an abelian extension. But when I adjoin these numbers to Q adjoin an I, then I always get an abelian extension. So this is a hint to how Kronecker's dream of use would be solved. It seems like you have to adjoin to Q adjoin I some special values of this transcendental function S. Okay, so this is kind of the origins of the theory of elliptic curves. We basically don't teach elliptic integrals anymore because it's actually kind of confusing. And then at some point you want t to be a complex number, and that's like mega confusing because it's like, what's the integral we're doing here? Well, it depends on the branch of the square root. Okay, but then what's the set of What's the Riemann surface for that square root function? Okay, great. Now we're into a little bit more modern mathematics. So what's going on? The modern interpretation is that square root of x cubed minus x, well, calculating it gives you a point on y squared equals x cubed minus x. So the real star of this show is not just one variable x, but two variables, an x and a y. And solutions to this polynomial equation in the complex numbers give you a complex manifold, which ends up looking like a bagel, like a torus, a curve as a Riemann surface of genus 1, we would say. So the Riemann surface with this equation, this affine equation, you have to add a point to infinity to it. It's got genus 1, and it's got a differential on it, dx over y. So in the previous slide, we were actually integrating dx divided by the square root of x cubed minus x, but that's just dx over y. And now if you believe that you can do calculus on such complex manifolds, then this is exactly what we were doing. We were figuring out what S inverse was. The input to S inverse was a point x comma y, and the output is the integral from that base point towards some point at infinity of this variable. And that kind of pushes the difficult, integrals of 1 over square roots into the background, and now we're just kind of doing something more abstract here. That integral, not well defined, because it depends on the choice of path. So why would it? The ambiguity is like, all right, I'm integrating on a torus here. A torus is like, it's not simply connected. There's loops on it. But there's a loop this way. Now, maybe I should actually be savvy enough to draw this in the slides themselves. So draw them on the board. I might use colors. If I imagine loops on this torus, here's one. And then here's another. There's other loops, of course, that can be made of combinations of those two loops. But I mean, if we're going to do some kind of integral from here to here, there's an ambiguity. Because I can go in some direct way, but I can also go around here, a loop-de-loop, and then go that way. And I'm going to get different answers if I do those two different ways. The answers are going to differ by an integral that goes around just this way, or some linear combination of those two. So there's an ambiguity in doing this integral. The ambiguity lies in a certain lattice. So I mean the z-span of two complex numbers. What are those complex numbers? One of them is our friend pi. The other one just happens to be I times pi. So doing the integral this way gives you pi. Doing the integral this way gives you I times pi. So what we end up getting is that this S inverse, it's defined, yes. So the inverse to this S inverse, the thing I'm calling S, is really going to be defined on this complex numbers, like this is target over here. But I have to quotient the complex numbers by the lattice. And that lattice is spanned by the pi and the I pi. So what's going on here, if I might add to this picture, is that here's the complex plane. I don't know what pi is, but I don't know what it is exactly, but it's somewhere there. It's a real number, and here's I times pi. And together they span this lattice. And when you take the complex numbers, so the function S inverse looked like this. We're trying to invert it. It looks like this. The function S inverse was multi-valued. Like it could take a value here, but then it's also going to take the value there. To make it single valued, I have to take this whole picture, it's the complex numbers, functioned out by the lattice so that these 2 points get identified. That means taking a square like this and saying, you know what, the edges of the square are identified, and the edges of that square are identified as well. When you fold up that square, you're going to get this kind of torus. So that's the logic behind this. So are there any questions on this picture? What kind of facts? TLDR, elliptic curves are elements. So regarding this particular elliptic curve, which is y squared equals x cubed minus x, let's suppose L is this one. So I'm going to call that pi times zi. And it kind of is. It's like every Gaussian integer multiplied by this pi. That is all this is. It's a square line. If I take the complex numbers, mod out by that lattice, I get E. And E is the set of solutions to this cubic equation in complex numbers. And the amazing thing about elliptic curves is that they are groups. And Alvaro demonstrated this. There's a way to think about that, the addition law on points of this curve. But you can also think of points on the curve as C mod L, points on this plane. You could add two of these and get another one. But basically, it's just the idea you could take an abelian group, quotiented out by a subgroup, and the result will always be a group again. So C mod L is a group. So that induces a group structure on E, and the two group structures we've been acquainted with are the same. So one interesting thing is that the group law, if you have one solution to this and then you have another, you can get a third solution. And that third solution is given by taking the original points and combining them as rational functions with rational coefficients. So basically, you can take, to get the coordinates of the new point, there'll be a numerator and denominator, and each of those is going to be polynomial in the old points. And the coefficients of those polynomials are all going to be. And you can suss this out just by staring at a picture where you have a curve falling on, you have a straight line falling on your cubic curve. It meets it in 3 points, and you can determine what's the relationship between the coordinates of these 3 points. So you could derive the space of that pretty directly. So here's a corollary to this. So if I pick an integer n, and I consider what happens when I take a point of E and I multiply it by n. And the result is going to be a rational function in the same way. Like if the inputs are x and y, the outputs are going to be rational functions in x and y with integer coefficients. And that implies this kind of fact before about being algebraic. Like if I plug in alpha to be a, I want it to be a point where it's like 1/n of the lattice. So, if n is 3 or something, I'm going to highlight some interesting points here. 1, 2, 3, 1, 2, 3, 1, 2, 3. And those are the points that are like 1/3 of the way or 2/3 of the way across or up. There's 9 of them. And if I hit this with s, then I land here. I get an x and a y. But then, since the two group laws are compatible, it means if I take a point here and I multiply it by 3, I get the origin. And that means, given this amazing fact, that the coordinates of those points were all algebraic numbers. So just by pure thought, we figure out this property that seemed kind of surprising, that this function, this s of alpha, actually is algebraic whenever alpha is a fraction of one of the endpoints, pi or I pi. So before I was telling you about s of pi over 2 or s of pi over 3, this explains why those are all algebraic. Does not yet explain why they're abelian over we would join I, but we'll get to that later. Questions on that? It's starting to ramp up. Okay, so back to this lattice. This lattice, I gotta say, it's special. It's super special. I can imagine a different lattice. This is made of squares, hey. I can imagine a different lattice made of rectangles. And this lattice has a symmetry that's not shared by all lattices. Like if I rotate this by 90 degrees, it superimposes the lattice on itself. And I could generalize it a little bit, just saying like, if I have any Gaussian integer whatsoever, I can multiply that Gaussian integer by the lattice, and it still remains inside the lattice. So think about geometrically what multiplication by a complex number does to a lattice. What does a complex number do when you multiply it into the complex plane? Well, if you write it in polar form, it's e to the I theta. That's going to stretch by r and rotate by theta. So I can think of that as a rotation dilation of the plane. And there's a special class of lattices where doing a rotation by dilation preserves the lattice. Most lattices don't have that, but this one does. So here's the definition. I'm going to say that L, a lattice, has complex multiplication by Zi. Well, we say that L, well, under this circumstance, when multiplication by an element of Zi preserves it like this. Generally speaking, a lattice has either, oh, so this means, oh yeah, I should have written what this meant. This means the set of all complex numbers that have this property. That collection of complex numbers is usually just integers. It's always true that I could take a lattice, multiply it by 7, and that superimposes on the old lattice. But that's not very interesting. I'm talking about when you get rotations involved, then it's interesting. The other possibility is that L has complex multiplication by what's known as an order in an imaginary quadratic field. That means a subring of the form Z plus Z eta. The eta here is not going to be a real number. Subring's got to be closed under multiplication. So if you think about what eta squared has to be, it has to still live here. So it has to be the root of a polynomial with integer coefficients. I might pause here and ask you, can you think of another way to draw this lattice other than square so that it has complex?
Another example or the same example in another way?
A truly different example. So it's easy to come up with examples because that are just simply symmetric. This one had a 90-degree symmetry. There is another example where there's a different rotational symmetry. This one's fourfold. We can also do sixfold. So what I'm going to do is draw an equilateral triangle, hopefully. Okay, best I can do. And I'm going to keep on drawing it out all the way around like so. And then I'm going to think about the lattice, where the lattice points are these guys. That's going to be the fundamental parallelogram, if you will, for the lattice. I can extend the pattern forever. And that's going to be an example of a lattice. What's this number? Let's suppose I label this as 0, and this is 1. What's this? Well, that's 120 degrees, and this distance is supposed to be 1. So use some trigonometry to figure out what point that is. It's -1/2 plus square root of 3 over 2i. So I might call that number. Great. So this is the lattice Z omega. And it has complex multiplication by this same thing, by the ring Z omega. So this is another example of a complex multiplication lattice. But you could, you know, that's a special property, isn't it? Most lattices are not going to have any such symmetries. These two are very special. When did I start?
44 months ago.
34. So I have 15 minutes?
Yes.
So, okay, so there's a relationship among lattices here. I might say that two of them, okay, the word is homothetic. So that means that you can stretch and rotate one lattice into the other. And it's a pretty obvious relationship among lattices. If I just stretch this one out and rotate it, probably the new lattice is going to have basically the same properties. Like all of the angles are going to be preserved. So great, that's called homotheity. Another way of saying is that the two elliptic curves are going to be isomorphic as complex manifolds. If I'm allowing myself homotheties, I can take, you know, my two basis vectors for the lattice and just scale one of them so that it's simply 1. And one of them is 1, and the other one can be wherever it wants to be. I can, if it's down here, I can put it above, and so that new, that other point, let me call it tau, lies in this region where the imaginary part is positive. We call that the upper half. One observation is that if I did a substitution on what tau is, and the substitution happens to take this form, where A, B, C, D is an invertible matrix with integer coefficients, then the two corresponding lattices are homothetic. And that's kind of an if and only if. And this detail isn't that important. I'm just saying that points in the upper half plane determine lattices, and you get the same lattice or homothetic lattices when the two numbers are related this way. So, you know, there's a whole group acting on, oops, no, manager. There's a whole group acting on this. And so this kind of quotient set, it's like this coset space, if you will, classifies all of the lattices up to this relation of homotopy. So this is an interesting complex manifold, and it's actually just the same as the complex numbers themselves because of the J-invariant. So I copied this picture from Wikipedia article for the J-invariant. And the input to the J-invariant is the element of the upper half plane. It will be invariant, the S will be invariant means under the action of these Mobius transformations. The output is the complex number, and this is a bijective map. And there's a nice formula for it. So the input is some tau. Plug in Q equals e to the 2 pi I tau, and there's like a whole series expansion for it. That goes 1 over Q plus 744, and then a whole integer value series in powers of Q. That converges for all values of Q that are less than 1 in magnitude. Elliptic curves are the same as lattices. So if a lattice has a J-invariant, then the elliptic curve has a J-invariant also. And there's a pretty nice formula for that. That's a little bit simpler. If you already happen to know that your elliptic curve has some equation, like this Weierstrass equation, then the J-invariant of that elliptic curve is just this rational function of the coefficients. Great. All right. Which lattices have this property of CM? So here's the deal. The following are equivalent. 1, the lattice has CM. It looks like this, or something else. 2, if the corresponding elliptic curve is called E, then E has some endomorphisms. It has some symmetries. The endomorphisms actually form a ring, and that ring is isomorphic to an order in an imaginary quadratic form. So the Gaussian integers or something similar. Another way of stating this whole thing is that the number tau in the upper half plane is fixed by some non-scalar matrix with integer coefficients. Like it's not changed under that Mobius transformation. And then it's pretty easy to see that 3 and 4 are equivalent. Tau, the last one would just be to say that this number tau is itself imaginary quadratic. Like you can write it this way. It's a plus square root of b, where a and b are rational numbers and b is negative. That's maybe the most down-to-earth condition. So as an example, when tau is I, you just get this nice equation that has CM by Z adjoint I. When tau is this number up here, E is this equation, and that has CM by Z adjoint tau. Both curves can be defined by equations with coefficients of rational numbers, which maybe you didn't expect on priori. All right, here are some examples of J-invariants, where we start to see some strange behavior. So this J thing is something rather transcendental in nature. It's some function given by a power series. When you plug in numbers to it that are, even if those numbers are algebraic, you certainly don't expect algebraic numbers to come out. But that's exactly what happens. So as an example, J of I, which is to say J of this lattice, 12 cubed, an integer. J of this number, this omega thing, 0, right? J of this number with negative 15 is this number, which involves square root of 5. And then there's our friend with 163. Then this integer comes out. So finally, this is connecting us to that weird phenomenon I was talking about at the beginning of the hour. And then I couldn't help it. So this is a discovery of Weber, a calculation. Square root of negative 14 works out this way. There's a root 2, another root 2, and then a root 2 embedded inside of another square root. So that means it's got algebraic degree. Its degree is 4. So it's an algebraic number. It's not a quadratic number. All right, there's got to be a pattern here, and that pattern is a theorem. I believe the theorem is due to Kronecker, and it was already. If the lattice has CM, then the J-invariant of the lattice is an algebraic integer. And furthermore, when you adjoin that J-invariant to Q adjoint tau, you get an Euclidean extension. So let's just focus on the fourth of these fact number 4, if we kind of take this for granted. So here's the formula for the J invariant in terms of this other variable q. Q is related to tau this way. If you do plug in tau to be this number, then okay, this part's pretty straightforward. You just do this plug in, and this 2 cancels with this one, and then you have e to the minus pi I, that's -1. The rest of it just puts the pi 163 over there. So that's negative e to the negative large-ish number, and so that's going to be a small, very small negative number. So let's substitute this q into the series, and just notice that all of the terms over here, they're actually going to be quite small. They feature powers of this tiny number q, so they're going to be very, very small, and the coefficients can't catch up. So what we get is that the j value, which is this integer, equals to 1 over q plus 744 plus some small negative number. And then you solve for 1 over q, or negative 1 over q, which is this guy, and you get this. So as long as you believe that the J invariant evaluated on this number is an integer, then you have to accept something like this. So this brings us down to the question of why on earth should the J invariant be an integer? I mean, why should it even be an algebraic number? Why should it be anything? It could be transcendental. The function is transcendental. But this is getting into why Hilbert's 12th problem is very interesting. So I have a more precise theorem about this. If the lattice L had CM by an order O, so O is like one of these two lattices, or any other, but then the J invariant of the lattice is an algebraic integer. And when you adjoin it, you get an abelian extension. But now I'm going to tell you the degree. The degree of that extension equals the class number. What's the class number? Here's the thing. The class number is the number of lattices that happen to have complex multiplication. There could be more than one. In both of these cases, there's only one lattice with complex multiplication by the order. In general, there could be. I'll just get to the point where I say what it means for the class number to be 1. When the class number is 1, there's only one such lattice. And it turns out that means exactly the same as saying that O has unique factorization. So bam, unique factorization is back on the picture. So this means that, oh yeah, so remember z squared of -5, that didn't have class number 1, it didn't have unique factorization. In fact, it has class number 2. There's 2 classes of lattices with CM by it. One of them is O itself, that's spanned by 1 root -5. That's what this notation means. And the other is spanned by 2 and 1 plus squared of -1. There's no way to like massage this. There's no way to homothety this into this, it turns out. And they both have complex multiplication by the same order. And those are the only 2. So that's goes hand in hand with the fact that that order didn't have unique factorization. So the following are now equivalent, given this theorem. The ring of homotheties of z plus z tau has unique factorization. 2, the J invariant on tau is just a plain old ordinary n. All right, still begs the question, why should the J invariant somehow have this magical property? So this is what I intend to do. A few slides, here we go. If you have a lattice with complex multiplication by an order, why on earth should the J invariant of that lattice be an algebraic? I have a little explanation for you, but it's all going to fit on this one slide. Here we go. Let's say we have an elliptic curve. Now let's say L and E correspond. L is the lattice, E is the corresponding cubic equation. So you've got your A and B. Like y squared is this. So elements of the order, they act on points of E through substitutions. Like x and y go to some other x and some other y. And those substitutions are rational functions in the original x and y with some complex coefficients. So there's an algebraic interpretation of what the CM means. There's some substitution that you can do that preserves the equation. When I read this proof, it utterly shocked me because I never could conceive of such a crazy thing. But here are the complex numbers. That's some huge uncountable field. Let's say we have an automorphism. such an automorphism could be crazy. You need the axiom of choice to construct lots of these things, but there could be one that sends the number pi to the number e because they're both transcendental. There's going to be tons of such automorphisms. Let's suppose we take E and we alter it via this automorphism. So we get a new such elliptic curve by changing the coefficients. And the J-invariant is going to be sigma applied to the J-invariant of the lattice, because the J-invariant of the lattice is the same as the J-invariant of E, and that's just some rational number in A and B, rational function of A and B. So then here's the thing. E sigma also has complex multiplication, in fact, by the same lattice, because elements of the order O, you can use the same formulas that describe what that action is, just with sigma applied everywhere. And all we're using is the fact that sigma is an automorphism of the field of complex. Now, this J-invariant map, the inputs are like homothetic classes of lattices, the outputs are complex numbers, but it's a bijection. So that means that if JL with sigma applied to it, that lives here, so there's got to be some lattice that lives over here corresponding to it, and it's unique. So there's a unique such lattice. And those lattices, that lattice has to have also complex multiplication, again by the same order, by the previous paragraph. So when you apply sigma to J of L, you have to get the J-invariant of a new lattice, which also has complex multiplication. But there can only be as many of those as there are the class number. There's only the class number of lattices that have complex multiplication by O. So putting this part all together, these two paragraphs, it seems that when I take an automorphism of the complex numbers and apply it to J of L, only H many numbers could come out. And the only possible explanation is that the J-invariant is an algebraic number of degree H. If it was a transcendental number like pi, then you could send it off to E or any other transcendental number you want. But since that's impossible, you can only conclude that the J-invariant is algebraic. So since J of L sigma can only take on H values as sigma varies, we conclude that it is actually an algebraic number of degree H. So that's sort of the proof in a nutshell of why it's algebraic. I didn't prove that it had to be an algebraic integer, but at least it has to be algebraic.
It's time.
See, ours is even better. These are something, yeah.
The arrows don't work well. You might have to scroll on the mouse.
Oh, yeah. Okay, great. Yeah, that's fine. So this may lead to the question of like, okay, orders in an imaginary quadratic field. So we made this amazing connection between orders and elliptic curves. And unique factorization played a really important role. So which of these orders have unique factorization? Are there any? If so, there'd be infinitely many prime generating polynomials, such as x squared plus x plus 41. Like lots of those. So what I'm getting at here is called the class number 1 problem. This was first considered by Gauss in 1798 in Disquisitiones Arithmeticae, and he conjectured the complete list. And one convenient way of describing what the order is just to say if the order is spanned by 1 and eta, eta has some minimal polynomial, and the discriminant of that polynomial determines the order. So if we consider the Gaussian integers, that's generated by 1 and then I is the root of x squared plus 1, and then the discriminant of that is -4. So we just call that the -4 order, and you can assign a negative integer to all these orders. So Gauss conjectured that the imaginary quadratic orders with unique factorization are all belonging to this one list. There's only finitely many of them. And the first one is -3, that's this one. The second one is -4, that's this one. and then it continues, and then the last one is negative 160. And that was conjectured in 1798, but the proof was not complete until 1967. I mean, Hagener gave a kind of description of the proof in 1952, but it was really completed by Steve in 1967. And the proof uses modular functions, which are, oh, I guess I didn't write this down, but which are basically like J-invariant. So the proof isn't just algebraic in nature, it really uses transcendental functions like this J-invariant. So the phenomenon kind of ends with 163. Okay, I'm over time, but that's fine. It's the last slide. Hilbert is said to have remarked that the theory of complex multiplication is not only the most beautiful part of mathematics, but all of science. Just really think about what Hilbert meant by this. And I'm getting a lot of this material from one of my favorite books on number theory. It has the odd title of Primes of the form x squared plus ny squared. But I learned a great deal of mathematics from this book. It's really fantastic. Thank you so much for coming to this talk.